and I'm an assistant professor at the Indian Institute of Technology, Delhi. We'll discuss two major topics in our poster. The first one is on the development of structure factor based deep LTO collective variable that we apply in OPIS simulation to study crystallization from melt. The second part consists of a method called constant chemical potential molecular dynamics that we apply in the study of crystal growth and nucleation from solution. Over the years, a plethora of collective variables have been developed for the study of crystallization. Our approach is based on an interesting property of a crystal, the structure factor. The full three-dimensional structure factor is defined in equation 1, where n is the number of particles, k is the scattering vector, ri are the atoms' positions. For a chosen simulation box, let's say a periodic cubic crystal, only a subset of L, M, N, which are integers, will contribute to the Bragg peak, where L is the simulation box length. And finally, the descriptors that we use are the square root of the structure factors. The representative structure factor profiles are shown on the bottom left panel for sodium chloride. The deep LDA method is a dimensionality reduction technique which has a feed-forward neural network followed by the linear discriminant analysis step, which is linear. The CV thus constructed was used in the recently developed enhanced sampling method OPIS to sample the crystallization events. A sample plumed input file is shown on the right bottom panel. We applied our approach to study the crystallization of two different systems. The first one was sodium chloride, and the second one was a simple molecular crystal, let's say molecular system, carbon dioxide. A large number of transitions from the crystal to the liquid phase or the other way around allows us to calculate the converged free energy profile. The CV profiles are shown in panel B, and they help us to calculate the converged energy profiles, which are shown in panel C, and two representative profiles, one for the liquid, another for the crystal, are shown on panel D. So this method is essentially very efficient in terms of studying crystallization from melt. Coming to the second part, while simulating crystallizations from solution, we often consider a finite size system containing a few thousands of particles. Such a small system suffers from severe finite size effects. During crystallization, solutes are drawn from the solution to the growing crystal. This leads to solution depletion. To grow crystal at constant solution concentration, Perego et al. Developed the constant chemical potential method in which the solution concentration near the growing crystal surface, let's say called the control region, which is shown on the schematic CR. The concentration in the CR is kept constant by applying a force, which is shown in the orange region on the schematic. That this force region acts as a membrane, which allows the solid particles to diffuse into the control region depending on the solution concentration, and thereby allows the crystal grows in the presence of constant solution concentration. The algorithm goes like, at first we calculate the number of solutes in the control region, and then the concentration, which is shown in equation 3, is essentially number density, and then you apply the harmonic kind of force to that concentration, instantaneous concentration, such that it remains close to the target concentration. So this method has been used to study the crystallization from urea from aqueous solution very effectively. However, at long time scale, when the crystal grows much larger, then the finite size reservoir depletes. To avoid such long time depletion issue, we developed the cannibalistic variant of the CVMD method. In this setup, one side of the crystal is grown in the presence of supersaturated solution, while the other side of the crystal dissolves in the presence of undersaturated solution. Since the simulation box has periodic boundary conditions, so the particles which come out of the solid particles which come out of the crystal on the right hand side, they can travel all the way from the right to the left hand side, and they participate in the growth events. So now a comparable growth and dissolution rates lead to a situation where the solution never depletes. So there is a kind of a circuit which is there in this event. So by doing so, by doing in this kind of setup, we could, when we perform the simulation, we observe that the solution concentration remains constant for a long time period. And from the growth profiles, which are shown on panel C on the left bottom, at 3 different concentrations, from the slope of these curves, we can calculate the growth rates, and those are plotted as a function of concentration on the right bottom panel at 2 different temperatures. So essentially, by running one simulation, you could calculate the growth as well as the dissolution rates without the solution depletion problem. And we thought that we can apply this similar kind of ideas to study nucleation. But in this case, the orthorhombic setup is not appropriate because we know during the nucleation, a kind of a spherical nucleus appears. So we thought having a spherical setup of the CMM method is beneficial for this kind of cases, for this kind of systems. So on the schematic, we have the pink region, which is the growth region where the nucleus will grow, and we apply bias such that the nucleus grows in this particular sphere, and then surrounding it we have concentric spheres, and we have the control region just outside of the growth region, and followed by another cell which is force region, and the rest of the box is a reservoir. And we applied this method to study nucleation of sodium chloride from salt solution. On the right top, we saw the evaluation of the CV, and essentially this is one well-tempered metadynamic simulation run. And on y-axis, on right top, we plot the collective variable as a function of simulation, well-tempered simulation, metadynamic simulation time. And it shows multiple nucleation and dissolution events. From there, we could calculate the free energy surface, which is shown on the right bottom panel. And so it goes from solution to the crystal, and we could identify the critical nucleus, which is somewhere in between the 2 basins. So this kind of method is useful to study nucleation from solution at control solution concentration. So in summary, we developed two methods. One was for the crystallization from melt, another for crystallization from solution at constant solution concentration. Thank you very much for listening to my poster, and I'd be happy to take questions. You can send me an email, and I'll be happy to reply to you by email. Thank you.